Welcome back. So we want to learn these values. I think it's best to be organized and not organize it into the two different triangles, but organize it in order 30, 45, and 60. So I made a table of sine, cosine, and tangent for 0, 30, 45, 60, and 90. Notice I've only gone through the first quadrant. I've gone from 0 to 90. Even though at the beginning I was like, oh, let's break these angles out of their right triangles. And then I just restrict everything to the first quadrant. And everybody's like, oh, Leach, you liar. But this is a good way to organize the information. We can see the patterns, and we can see how things are going to increase and decrease. This is going to be helpful later on when we start applying trig functions to real numbers, not just angles. So here we've organized things. I put the angles in order, so 30, 45, 60. And then I also put a 0 and a 90 at the beginning and at the end. Notice that the sine of 30 and the cosine of 60 are equal. That's because of the cofunction of complementary angles are equal. So sine of 30 is a half, cosine of 60 is a half. What that means is that those four are linked together. Sine of 30, cosine of 30, sine of 60, cosine of 60. And it's really only two numbers, 1/2 and √3/2. So those four, you really only got to know one of them. If you remember that the sine of 30 is a half, that will help you remember that cosine of 30 is √3/2. And if you got those two, you get the other two kind of for free. Sine of 60 will be √3/2. Cosine of 60 will be 1/2. So if you just remember what your choices are, 1/2, √2/2, √3/2, you can cut down on the amount of things you have to remember. Sine of 30 is a half. My other choices are √3/2, √2/2. Then we just have to remember that √2/2 is the one that matches with sine and cosine. That's where sine and cosine agree. And we know that that happens at 45 degrees. So sine of 45 is √2/2. Cosine of 45 is √2/2 as well. Tangent is a little bit different. There's a √3/3, a 1, and a √3. One of the things that might help a little bit is to know the decimal approximations of each of these values. So 1/2, that one's easy. That's just a 0.5. √2/2 we saw earlier is 0.7071. √3/2 we hadn't calculated, but the square root of 3 divided by 2 is 0.8660. We had previously looked at 1 over the square root of 3, which is the square root of 3/3, and that's 0.5774. And the square root of 3 is 1.732. So it would be useful to recognize the decimal approximation of the values that you're trying to remember. That way, if you forget, you can always just go to your calculator and say, what's the sine of 45? 0.7071. Oh yeah, that one's square root of 2/2. Notice I put on two more columns. I put on a column for 0 and a column for 90. We're not going to do anything fancy here because we haven't gone back to our standard position, but sine of 0 is equal to 0. And the sine of 90 is equal to 1. So we could see the pattern in the sines. Sine of 0 is 0 and then goes up to 1 in that first quadrant. 0 and then 0.5 at 30, 0.7071 at 45, 0.8660 at 60, and then 1 at 90. Cosine just goes the other direction. As a co-function, complementary angles. Cosine of 0 is 1, and the cosine of 90 is 0. So cosine is just going the other direction, starting off at 1 and dropping down to 0. Organizing things this way is helping us remember these values, and it's going to further help us later on when we start graphing these functions. When we get to tangents, tangent of 0 is no problem. All is fine there. So we go to 0. It's tangent of 0 is 0. Tangent of 30 is 0.577. Tangent of 45 is 1. Tangent of 60 is 1.372. So we can see that tangent is increasing in this first quadrant. Weird things happen though when we get to tangent of 90. So when we ask the calculator, what's the tangent of 90? The calculator is like, oh, dude, what are you doing to me? This is because the tangent, as theta approaches 90, tangent is headed towards infinity. That's pretty weird. So it's undefined. It's undefined because it's approaching infinity. So it's undefined, it's approaching infinity. 90 is not in the domain of tangent. I've just brought up the concept of infinity. It's a little bit early for that. For those of you going on to calculus, this is going to be everybody, because everybody's going to turn into math majors. Right? Yeah, everybody's going to be math majors. I'm just kidding. I get like 1 to 2 math majors per year. I'm like, oh, who's going to be a math major? And like one person raises their hand. This is out of all my classes. I got Calc 2, Calc 3, trigonometry. I probably have 1 math. Because enrollment is down. If I had 3 full classes, outside chance of 2 math majors, so it's probably 1. Most of you is going to be like engineers. Because no one knows what mathematicians do, but engineers make money. So if you're going to be an engineer, by the way, yeah, you will make money, but divide by the amount of hours you're going to have to put in to do that. So just don't do things for the money. Anyway, calculus is where we actually start studying infinity. But we can actually get a pretty good idea about why tangent of 90 is going off towards infinity. Remember, tangent is opposite over adjacent. So if I build a triangle, a right triangle with an angle theta over here, here's the opposite. And if I fix the adjacent, let's say at 1, then tangent of theta is opposite over adjacent, which is 1. What happens as we start to open up this angle theta, as we open up this angle theta, the opposite starts getting taller and taller and taller. Can you see it? I should have animated the whole thing. I should have like a video animated, but we're not going to do that because I don't have any animation skill. And we can see tangent starting off at 0. If theta is 0, then opposite is 0 because this is a flat triangle. But then as theta increases, when theta gets to 30 degrees, we're at 0.5, the opposite is going to be 0.5774. When theta is 45, then the opposite is going to be at 1. When theta is 60 degrees, the opposite is going to be 33 or 1.732. We can see the opposite increasing as theta increases towards 90. The problem is if we let theta go all the way to 90 and we only got 180 degrees to build a triangle, we no longer have a third angle at the top. We can't have a triangle with two angles in it. We can't have a 0-degree angle. And so as theta gets close, this hypotenuse gets closer to vertical, the opposite just keeps getting bigger and bigger and bigger. So that if we let theta go vertical, then the opposite goes towards infinity. This is because this class takes place in Euclidean space. For those of you who are wondering if this is always the case. Any questions? We're not allowed to have two 90-degree angles in a triangle because the sum of the angles has to be 180. And we can't have a 0-degree angle. What does that even mean? How does that make sense? We can do that. We just need a completely different version of geometry. Any questions? Is everybody okay? Euclidean geometry is the one that we most deal with. If you've been in a geometry class before, you are studying Euclidean geometry. Here's the difference. This is not relevant to trigonometry, so if you want to tune out, this is the time to do it. Of course, most of you are like, oh, dude, 1 o'clock is the time to tune out. I've had my camera off this whole time. I have the ultimate college student skill. I can sleep with my eyes open. And I can take it a step further. I sleep with my eyes open and my hand just kind of like slowly moves like it look like I'm taking notes. But you're like, oh. That's the ultimate college ability. But Euclidean geometry, Euclid said, all right, if you got a line and a point not on that line, there is only one line through that point parallel to your original line. That's Euclidean geometry. Euclid says just one parallel line. Euclid says there's just one parallel line. The other geometries say, given a line and a point not on that line, there are an infinite number of lines parallel to the original line. Then the other side of that, given a line and a point not on the line, there are no lines that are parallel to that. Two different kinds of geometry. Well, three, including Euclidean, which is the one that we normally study. Any questions? All right, so we can see that increasing that angle theta increases the size of the opposite side, but theta can't get all the way to 90 because that opposite side would have to be infinitely long. And we have to have a 0-degree angle in our triangle. Dogs and cats living together, mass hysteria. So notice that I'm only asking you to remember the values for sine, cosine, and tangent of 0, 30, 45, 60, and 90. I just want you to go through that first quadrant. But the whole brief for this particular talk is getting our angles out of the first quadrant. The reason that we can get away with this is that the second, third, and fourth quadrants are pretty much just copies of the first quadrant. All the triangles are going to look the same. Notice that on the previous page, I had these three angles, all with a reference angle of 60 degrees. If I make right triangles, they'll all be 30, 60 right triangles. They'll be in different quadrants, but they'll all be the same triangle. So that 120, the 240, and the 300-degree angle are all related to that 60-degree angle. So if we can know that 60-degree angle really well, we can just take the values that we have and put them into the appropriate quadrants. Any questions? Now all we have to do is learn sines in different quadrants. Oops. Now you have to learn sines of trig functions in different quadrants. So let's do that. In the first quadrant, all are positive. In the second quadrant, sine is positive, cosine and tangent are negative. In the third quadrant, tangent is positive, sine and cosine are negative. And in the fourth quadrant, cosine is positive, sine and tangent are negative. So rather than knowing 9 different things, I prefer to summarize this by saying what's positive where. So we summarize this by saying what's positive where. All are in the positive in the first quadrant. Sine is positive in the second quadrant. Tangent is positive in the third quadrant. Cosine is positive in the fourth quadrant. So this is what we're going to remember when we need to know what's positive where. I haven't even really explained what I'm talking about when I say what's positive where. But what I mean is that in the second quadrant, the sine of any angle in the second quadrant will be positive. The cosine of any angle in the second quadrant is negative. The tangent of any angle in the second quadrant is negative. And so on. In each quadrant, aside from the first where everything is positive, there's only one that's positive. So it's convenient to remember what's positive where. If you remember what is positive, that'll help you remember what isn't positive. So just remember what's positive where. A, S, T, and C. Sometimes people remember this as all students take calculus. I like to phrase it that way because y'all are going to be math majors, I can tell. I don't know what kind of math major you're going to be. Some of you might be applied math majors. If you really want to flex on people, you'll get your undergraduate degree in applied math. I'm pretty sure it's the most difficult one. I don't have a degree in applied math. I got a degree in what's called pure mathematics. Mostly because applied math, I would have had to learn how to talk to computers, and I just didn't want to do that. Computers are really annoying. They're so dumb. I just compute stuff. bio major, you're gonna have to take calculus. And during calculus class, you're gonna be like, oh, why am I here? Some of you are gonna be chemistry majors. Like, well, why am I in this calculus class? I'm a chemistry major. I just want to cook crystal meth. I saw that on TV. And then you're like, well, hang on a second. Did you watch the whole series? No, I missed the last season. Why? No reason. All right. Any questions? We had 3 big things today. Some angles that we need to know. 30, 45, 60. Actually, 0, 30, 45, 60, and 90. I want sine, cosine, and tangent of each of those 5 angles. That was like 15 things to know. Look for the patterns in there. Know how to take an angle from standard position and figure out what the reference angle is. And then learn what's positive where. Those are 3 big things that we need to put together. So we'll put these together next, or what's today, Tuesday? Today's Thursday. We'll put these together next week on Tuesday. So this weekend, your job is to learn those 15 values, learn what's positive where, learn how to get your reference angles, and then try to figure out how this is all going to get put together. Any questions? Comments? All right, that's going to do it for today. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing. Make an announcement, okay?